Okay. Hello, everyone, and welcome to the fourth meeting in the Cyber Seminar Series, Critical Conversations, Why Integrative Earth and Environmental Science Might Define Your Future. This unique series was convened in collaboration with the Critical Zone, RCN, and the National Association of Geoscience Teachers, as well as Quasi. My name is Julia Masterman. I'm the Science Education and Outreach Coordinator for Quasi, the consortium of universities for the advancement of hydrologic science. Our mission is to advance water science by strengthening interdisciplinary collaboration, providing critical infrastructure through our data services, and promoting education in water science at all levels through programs like this Cyber Seminar Series. I'd encourage you to reach out to me, visit our website, sign up for our newsletter, or join our community Slack channel to learn more about what we do or to get involved. I'll add information on all of those things in the chat in just a moment, and there'll also be other resources being shared in the chat throughout the webinar today. Before we get started, a few logistical things. Firstly, this main session is being recorded. You're welcome to turn on your video if you prefer, but please note that in doing so, you are agreeing to appear in the recording that will be posted on the Quasi YouTube channel later this afternoon. Secondly, later on in this session, we will be breaking out into breakout rooms. The breakout rooms will not be recorded. And finally, you'll note that this is a meeting and not a webinar. This is intentional, and we're looking forward to engaging with you all during the breakout sessions. We ask that you be respectful of everyone in this meeting and remain muted until we are in the breakout rooms. Please ask any questions you may have during this main session via the chat. If you do notice any unacceptable behavior, please use the chat to notify me. Again, my name is Julie Masterman, or one of the other hosts. This webinar is the fourth in a series of 6, and will be running through the end of this month. You will need to register for each individual webinar to attend each week. So if you haven't already registered for the last few, please do so visiting the link in the chat, which will be there in a moment, to register for each individual talk. Please also spread the word about this series to peers and colleagues. Share the link and follow at Join CZ Science and at Quasi on Twitter. The recordings for the previous meetings in this series can be found on the Quasi YouTube channel. So thank you again for joining us this week for an introduction to LIDAR in CZ Science, and we look forward to hearing your thoughts during the discussion at the end. And with that, I'll pass it on to Kamini.
Great. So it is with my pleasure that I get to introduce Adrian Harpold today. He is at the University of Nevada-Reno and is part of this series in helping to introduce new topics to people that are interested in earth and environmental science. He is going to talk about LIDAR today, and then we'll have some cool breakout rooms at the end of that. And then at the end of the breakout rooms, we'll come back for just a quick close at the end. So with that, I'll hand it over to Adrian.
Thank you, Kamini. Does my screen look correct?
It does look great. Yeah, looks great. Okay.
I am really excited to be joining you from Reno, but excited to be here, or wherever you are, and invited by this great group. I am an associate professor at the University of Nevada in Reno, and involved with critical zone science going back to 2010 or so, and you'll get a little bit of my backstory through that. And I'm currently working on a project about dynamic water storage led by Dr. Holly Barnard, and a project about critical zone resilience led by Dr. Julia Perdriel. And so very actively involved in this, and just can't wait to tell you a little bit about LIDAR. So what you're going to get today is a sort of weird mashup of critical zone science and my interests in hydrology and forests, a little bit about my philosophy of approaching a new technology and what it takes, and hopefully a bunch of eye candy and interesting visuals to get you excited about this topic. So I'll start with the take-homes here, because I don't want folks to lose sight of what I'm trying to tell you. We're not going to go deep into the science too much in about 15, 20 minutes. So I'm going to really tell you about the value of learning a new technology and why you might want to be part of that, with lidar as our example. Why that can be hard, and some tips that I've learned from working on this topic of lidar for the last 10 years or so. And then some ways that you can make more of an impact by being incisive and inclusive. And to get us started here, we'll show some images of why something like a lidar technology is valuable. We can look down from an airplane and be able to map individual trees as a height model, take those trees off and turn it into an elevation model or a bare earth model where we can see the roads going across the landscape. We could see boulders and trees on the ground. And then if we fly over again in the winter, we can map the snow depth of the same area and learn something about the hydrology. So this technology of lidar is particularly valuable for critical zone science. And it really has a history rooted in defense and technology, and has been brought to the earth sciences. And the correct pronunciation and spelling is lidar, all lowercase. I've learned this the hard way working with some of the top people in the field. This is sort of the accepted nomenclature, although you'll see it sort of capitalized and spelled in different ways. And it's basically very similar to what you would have with a rangefinder in your garage, where you shine a laser, there's a time of flight, and you get a distance back based on how long the laser took to bounce off that object. Of course, it's a very sophisticated version of that, where you're actually sending out a pulse of energy and you're getting a waveform of energy back. And we're taking that waveform of energy that's illustrated here on the height axis. It says relative signal. That's basically the amount of energy coming back. And we're discretizing that into these individual returns that you can see illustrated with the plane flying over. So we're getting these returns of energy back. We're measuring the distance of those energies with time of flight, and it's allowing us to map the vegetation, see through the vegetation. It's not dependent on shadows or clouds, although flying with clouds is not ideal. You can fly at night, and it really produces a data set that's really useful for a variety of purposes. I'll try to illustrate. Okay, so lidar in the context of learning a new technology. And lidar, I think, is a good example case of the challenges and opportunities of a new technology. And I always find this example of Bell's law kind of the quintessential technological paradigm, right? Where the size of the computer that's producing effectively the same computations is getting smaller and smaller by orders of magnitude. So 10 times roughly per decade or so, right? So our computers that are on our phones are now equivalent to things that took up rooms just a few decades ago. And lidar is very much the same trajectory. And I'm particularly reference your eye to the green line here, which is the number of pulses or times that laser light goes out. So if you were clicking your rangefinder, it'd be the number of times you click it. So 250 kilohertz is 250,000 times per second, right? So we've started just a couple decades ago with units that were only mountable in aircrafts, could take about 5,000 points per second. And now we're easily operating units that can collect 2 million points per second. So the technology is ramping up. This gives just tremendous opportunity because now the units have gotten smaller. We can put them on fixed wing aircrafts, helicopters, unmanned aerial systems. There's also terrestrial systems that sit on tripods. And these all have advantages and disadvantages. And so the National Center for Airborne Laser Mapping, that's here today. I see I spelled their acronym incorrectly. I'm sorry about that, Craig. manages these kind of suite of instruments that we can use to measure things like critical zone structure. And what is so powerful about something like a lidar technology? It's that it's measuring the whole suite of structural characteristics of the surface. And I'm going to try to illustrate this in a series of figures that we made for a paper a number of years ago at this point, showing a variety of processes. Think of these as critical zone processes. First, I'm going to show processes focused on the ecosphere or ecosystem processes. And on our horizontal axis is space scales. So like 1 meter here, 10 meters, time scales. And so you can see these ecological processes like biomass storage and transpiration happen over longer time scales relative to nutrient flux and habitat. And illustrated in these colors here are all those different ways we can measure with lidar. So with airborne systems, potentially with spaceborne systems that are now coming online, and we can measure these processes that are important for ecosystems. But what's so neat is we can take that same set of measurements and we can also extract information about the geosphere or geological processes. And so this is showing things like bed load and riverbed evolution, surface formation and channel incision, spanning across the same space and time continuum. So with that same information, we're overlaying these different processes. The last one I'll show you is hydrological processes. So the one I think about quite a bit. So things like in-channel flow, evapotranspiration, groundwater flow at longer timescales. So the potential to link these spheres with the technology of lidar is what makes it so powerful for critical zone science, and I'll give some examples. Okay, so pivoting back now to thinking about, again, lidar as an example of a technology. Why would you want to spend, in my case, 10 years incrementally learning a technology? How is that going to advance your career, make your job more enjoyable or impactful? I'm going to give you some examples here of my path that I think will be helpful. I've been really more of an applier of technology. This is my sort of conceptual understanding here of, there's a lot of folks that are developing the technologies. They're really the makers of the technologies. They're building the laser systems. They're figuring out how to put them onto airplanes. They're developing the software that collects those measurements. Often these are engineers and software developers working for companies. The appliers of those technologies are often scientists. And I think this is where science really has an opportunity. So whether you're collecting new data in a new place, maybe you're applying a different method in a better way, or you're taking the data and you're making it more accessible in some way. This is a really useful place to be a scientist using a technology. And then I'd say there's even farther down the sort of technology chain are the end users. So a lot of people might just download lidar data to help with a background image or do some kind of very simple calculation. So they're not really applying the technology, they're really just sort of using and taking advantage of existing information. So why learn a new technology? It's a new tool in your toolbox. And I will say in my case, and the examples I'm going to show, it's really taught me a lot about critical zone science. And it's improved my scientific impact. It's allowed me to build a community of people that I'll introduce you to today that I've met now over 7 or 8 years ago. And it still remains exciting to see the new technologies coming online, the new data sets. Why you can't, take all of this on is because you can't become an expert in everything, right? You need to find the technology that interests you, that you see a path forward in, that really excites you. And, because it's a technology, there are going to be big changes. Things may even completely go out of date. So you need to recognize that going in. And it really will take some persistence, some personal persistence, and a network of mentors and collaborators. And I'll focus on some of this for the rest of the talk. So the points I want to make here about my experience using LiDAR was that I needed to be in the right place at the right time. I think there's some aspect of that for a technology that you don't get to control when it becomes mature. And you really need to build a network. You need to develop some skills. You want to find somewhere simple to start, and you want to learn how to be incisive and inclusive in the science that you do. And my luck was really starting a postdoc with Paul Brooks at the University of Arizona in 2010. I knew almost nothing about snow. I had no experience with LiDAR. I don't think I knew what it was, or had just vaguely heard of it, and was in a position where there was a critical zone project that had just started, and they were flying LiDAR in the previous summer and then in the winter that I got to go out. And this site in the Jemez River Basin in northern New Mexico is just an incredible place with an incredible cultural history, and it's an extremely important historic or ancestral site for local Pueblo and the Jemez people. The history there of habitation and burning prescribed fire is just amazing. It's a place that I found just very beautiful, and spent quite a bit of time up there, and really got to see the system from the ground as we were starting to do this LiDAR work. So the year after the LiDAR data set flew, there was a very, very severe fire. We had just moved up there and moved back down to Tucson. This fire broke out and devastated several 100,000 acres. And it was my sort of first realization that this LiDAR data set was, a potentially time-sensitive opportunity, right? So there was work to refly the area, and we went out and did snow surveys. And we were able to go out that following year, 1 year after the LiDAR data was flown. And I'm showing you a ratio here that's the snow water equivalent to the amount of precipitation. So think of a bigger number here as more snow on the ground. So before the burn, these two areas that were flown by the LiDAR had about the same amount of snow. However, after the burn, the site that was severely affected by fire, shown down here, had less snow. So we were able to use the LiDAR data sort of immediately after it was collected to help us better understand post-fire snow hydrology. And the opportunity to do this was really just about kind of being there when the fire happened. The LiDAR data sets were there. But I also think there's some ways that you can position yourself by developing scripting or coding tools like R or Python. I unfortunately work in MATLAB. The math background that supports some of this, and discipline-specific knowledge, whether you're a soil scientist, a geologist, in my case, a hydrologist, the ability to have that knowledge, that core knowledge that you can apply to the new technology. So one of the successes I think I've had, well, let me say it this way. I think all the successes that I've had with LiDAR have really built out of a network of people. You are not going to be able to teach yourself all of this, yourself, and you need a network to bounce ideas off of, improve your ideas. And this network has proven, basically all the folks that helped me organize this are still close collaborators. So in 2014, I organized a workshop in Boulder, Colorado, with the idea of uniting ecologists, hydrologists, and geomorphologists and geologists around this idea of what can we do with LiDAR to advance critical zone science. And here I'll highlight our esteemed team today. There's Dr. Nancy Glenn in the back there, Dr. Joe Marshall here in the and next to me, and then Dr. Craig Glennie in the back, and Dr. Tyson Swetnam. Yeah, so long ago, Tyson and Jill, I do not think were doctors at the time. And this team wrote this really excellent paper that I've already shown a few figures from. And our point was that we have this ability to look at ecological information, hydrological information, and sort of geological or geomorphological information all at the same time with LIDAR. But there really are few studies that are doing that. We're all kind of often sitting in our own disciplinary silos, right? We don't often look as far outside of our discipline as we should, and we're missing opportunities. So what I think is interesting about this is it really highlights both that critical zone science and LIDAR offer an opportunity for more inclusive science and research. Yeah, and I'll point out Dr. Noah Moloch, who was my postdoc advisor at the time. And he really helped me figure out that, you know, you got to start somewhere simple. You can't do everything, right? We had this incredible data set of LIDAR all over the West, but I was really green to what to do with it. I didn't really know what to do with it. So what we did was we spent many hours getting the data set together and just publicly releasing it to the world. And while this at the time didn't feel as satisfying as making some kind of major scientific breakthrough, I now realize, you know, spending that time made me better understand the data. And it also put this data set out there, and it's been used by a lot of other folks. That time, flying around in LIDAR, you know, GIS, Geographic Information System, another tool that's useful, and just looking at the data a lot, being in the field, walking around, looking at patterns of snow and trees, you start to sort of have an instinctual understanding for these patterns. And LIDAR was able to show us these really strong patterns of ablation or loss of snow on the forest edges, other places where we had extra accumulation of snow. So these really fine scale, these are basically individual tree scale differences, right? Snow on one side of a tree, but not on the other. So much information there. What could we do with that information? So it took years to sort of think this through. Several years later, probably 5 years after the data set was collected, I got the lucky opportunity to work with Dr. Patrick Broxton, who's at the University of Arizona. Patrick is incredibly talented modeler and coder, and developed a 1 meter wide model that represents basically tree scale. So we can apply this over a whole landscape and represent the energy and mass of snow fluxes across a whole landscape, but control for individual trees. So we can capture some of these processes that I saw were so important or so apparent in the LIDAR data. So this is an example of the LIDAR observations of snow depth. Some of this I was just showing you, where you have shallow snow depth along the edge of the tree, because that south-facing edge warms up and melts that snow. And this model is able to reproduce that to some degree. So we've developed this fancy model using the vegetation information and topography from the LIDAR, and then comparing it to the snow. What does this let us do? Well, 10 years after starting, you know, down this path of snow and forests and LIDAR, we're finally kind of answering some of what I think are the really important questions for society, which are, what happens after a really severe fire to snow? And we're able to show this really severe fire that some places gain snowpack in yellow and some places lose snowpack in blue. So our model allows us to understand what fire will do to snow in ways that we wouldn't be able to do by collecting the measurements ourselves. Another example of something you wouldn't be able to do yourself is go out and thin a forest in Lake Tahoe and try to understand what the snowpack is going to do. But now that we have a model, we've learned, we've trained this model with the LIDAR data, we can virtually thin our forest and we can run our snowpack model, we can understand where there'll be more and less snow and take that information to managers. Okay, I got one more example for you all, trying to get you excited about the possibilities here. So another opportunity that was sort of presented to me soon after I started here in Reno was to work with the NASA Airborne Snow Observatory. This is a group led by Tom Painter that's now an independent corporation where they fly an airborne lidar unit. And they came out to our site here near Truckee, California, just an hour or so away from where I am. And they flew this watershed where there's much, much more snow on the top of the watershed and blue, less snow down the lower part of the watershed. And we can zoom in on this red box here, and we can see all the dynamics of information that are present. So deep snow hidden in the trees, shallower snow on the edge of the trees, no snow in the open. How do we take this information and say something about how much snow is under the trees? So working with a postdoc, Tiho Kostanov, we developed a method where we mapped snow under the trees. And I won't go into the details here, but we had to account for the fact that you can have low branches and low trees. So there can be times where you're confusing the snowpack for a tree, but we were able to map the snow under the tree. And then using that information, we can go across a whole bunch of LiDAR sites that are, some sites that are warm climates, some sites that are cold climates, and we can show that snow disappears more quickly under the canopy of a warm climate forest and in the open in a cold climate forest. But we can do it in a way that would never be possible if you were out like Roses here with a snow survey stake, where you're making these measurements manually and you might collect a few hundred. Now we're able to make many millions of measurements across, great elevation gradient, large elevation gradients, and show these patterns in ways that really haven't been able to be shown before because of this LiDAR technology. Okay, so to wrap up that sort of wide-ranging talk, new technologies are really going to help advance science, and our ability to be part of that, I think, is exciting. So if you seize that opportunity and you are sort of nervous and excited about it, I think that you can turn it into something that maybe will last through your career. But it does require quite a bit of work, persistence, and for certain, a network that can support you, and hopefully over time, you can give back to as well. And I think that you can't understate, your ability to be creative in this field and to be, learning and growing along the way. And so sometimes you got to start simpler than you want to, but over time, as you learn and grow, you can take that and your sort of unique understanding and interests and be creative and develop things that other folks haven't developed before and help advance critical zone science. So with that, I will, I guess, turn it back over to Kamini.
Sure, I'm happy to take this. So what we're going to do now is we're going to move into these breakout rooms.